In this example, we are going to solve the thermal modeling of a cylindrical lithium-ion battery in a 2D modeling. So first of all, we are going to download all the required files. And then after that, we'll open console and the PDF file, which has all the required instructions to follow the simulation for this tutorial. For this example, we are going to simulate an air-cooled cylindrical lithium-ion battery during a charge-discharge cycle followed by a relaxing period. In this model, we are going to use the lumped battery model, which is different than the lithium-ion battery model which we used in the last video. So for the lumped model, we need some information or some initial input, okay, such as the battery capacity and the initial state of charge, and also in addition to some experimental data that need to be fed to console. So in this model, we have no idea what is the chemistry for the anode and the cathode. Okay, so we are only using some of the experimental data in addition to some of the assumptions and inputs as well. And here are some of the required information to be able to perform this model. And for this example, we are going to produce these results. First of all, we are going to have the cylindrical cell, and then we'll be able to get the minimum and maximum temperature, which varies with respect to time. And lastly, we'll be able to get that charge-discharge curves in this way. Now, to start the instructions, we'll start from here, the beginning. So we'll go to the model wizard, and we'll use 2D axisymmetric in this case. And we'll choose the batteries and lumped battery. And for the studies, we'll select time-dependent study, and done. For the geometry, there are two choices. The first one is to use the console file, which is provided with this tutorial, or we can do it from scratch, and in this case, I will do it in this way. So we are going to create the geometry, and the geometry starts from here. Okay, so we are going to skip the new because we already have a model, and for the global definition, in this case, we are going to load the parameters. And now we don't need to add a component because we already have one component in this case. Okay, so we are fine. So we can skip this step and we can move to the geometry. So we'll start with the first rectangle. We'll go to the geometry and rectangle. And for the width, it's going to be the radius of the battery and the height of the battery. And we'll expand the layers, and we are going to have two layers instead of one. The first layer will keep it as it is, but it's going to be the diameter of the canister. And the second layer will be used to specify the thickness of the canister. Now we can click Build Selected, and we'll draw the second rectangle. And this one is for the mandrel. For the layers, we are going to have only one layer, which is for the mandrel. And in this case, we are going to have the layer to be on the left-hand side. So we're going to clear the layers on the bottom, and we'll select or check the layers to the left, like this. Now we will add a mesh control edges, which is helpful later on when we do the meshing for this geometry. We'll go to the cleanup, virtual operations, and we'll choose mesh control edges. And we're going to select the following edges for this one. The next step now is to go to the selections and explicit selection. The first one will be for the battery can. And this will be for domain number 1. And we are going to repeat this process for the other two domains as well. Now we have the geometry ready, and we can go back to the beginning of the instructions. So after building the geometry, so we'll go to the next step, and we are going to import the required parameters to perform the simulation. After that, we are going to create a waveform which will be used for the applied current, and we'll select the functions and we'll go to the waveform, and we'll specify the type to be square. The angular frequency will be 2π divided by cycle time. Now we'll add a variable for the applied current, and we are going to use this function. So you can just simply plot this function to see what it looks like. We will add the variable, and the expression will be like this one here. Okay, the meaning of this expression is the following. We have LB, which is the lumped battery, this one. As you can see here, this is the lumped battery. And so we're specifying that it is a 1C current rate for a lumped battery. This is a 1C rate, and we're multiplying that by 7.5. And the way how we want the current to behave is by using the waveform function, which we defined earlier, which is this one. This will be applied as long as the time is less than 1500 seconds. Now we will create probes. Probes are important to be able to monitor the change of a variable during the simulation. And in this case, we are interested in the change of temperature. Okay, and the probes which we are going to do now are important to be able to plot this graph. In this graph, as you can see, we'll be able to know the minimum, maximum, and mean temperature at different time intervals. And to be able to do that, we'll need to use probes. Starting from the mean temperature, we'll go to the definitions and probes, and we'll select domain probe, and we'll change the label name to be mean temperature, and the variable name will be mean T. For the source selection, we are going to select active battery material because we are mainly interested in the temperature change in the active material, as it is the source of heat in this case. And for the expression, it will be T minus T initial. And what does that mean is the following. T is the temperature of the active battery material during the simulation, minus T initial, which is, let's say, the room temperature, which we already assumed in the parameters here. Okay, so let's say we started the experiment at 25 degrees Celsius. So at time that's equal to 1 second, at that time it will be T minus T initial, which will be 0. So for that reason, when you go to this graph, you can see here it starts from 0. Now to complete this probe, we are going to expand the table and window settings, and we will add a plot. The purpose of adding a plot here is that when we are done with the simulation, a plot will be created by using these probes. Now we are done with the mean temperature, and we'll duplicate this one to create the others. And for the probe type, in this case, we're going to change it to be the maximum, because we're interested in the maximum temperature within the active material in a specific time. We will repeat the process for the last one now. After that, we'll add the material which is required for this simulation. We will add this material to the component. This material will only be applied to the battery can. After finishing with the materials, now we'll be moving to the lumped battery model. The lumped battery model should only be active for the active battery material. So we should exclude the mandrel and the battery can. And now we will define the current and the capacity and the state of charge for the battery. After that, we will move to the cell equilibrium potential, and in this case we will use experimental data to fit COMSOL with the required information to be able to generate the equilibrium potential of the cell. As you can see here, there are two tables. The first one which relate the state of charge with the open circuit voltage of the cell, and the second one relates the state of charge with the temperature derivative. And we need both of them to be able to continue with our simulation. This information is available in the tutorial files. So in this case, we are going to import these data. So we must first clear the tables. And now we can load the data. Now we will have to provide the required information for the voltage losses. As you know, we have the ohmic over potential, activation over potential, and concentration over potential. So we'll provide this information. And we will include the concentration over potential. Now note the following. These overpotentials are not available for us. What we usually can do is the following. We can use an optimization model which can estimate these overpotentials. And unfortunately, we cannot access the optimization model on the current license which we have. So we are done with the lumped battery model, and now we'll be moving to the heat transfer and solids. And in this case, we will go to the physics and we will add a domain that's related to the solid phase. For the domain, it will be the battery active material. And now we will provide the information for the thermal conductivity. Note the following. We need to change this one to be user defined because in our case, we don't know what's the active material within the battery. So if it is a lithium-ion battery, so what's the anode and the cathode and the electrolyte? So we have no idea what's going on. So we only have the value for the thermal conductivity. So it will not be from the material. So we'll specify that from the parameters. And since this is a cylindrical cell, so we are going to choose diagonal. And we'll specify the radial and angular thermal conductivities. We will finish this part with the density and specific heat. Now we will add a domain for the mandrel. And we will type in the associated information. After that, we'll add a heat flux. And for the boundaries, we will select the outer boundaries in this case. And we are going to have a convection heat flux with a heat transfer coefficient of 20 watt per meter square Kelvin. And we'll define the external temperature to be the initial temperature of the air. To make sure the model is set up correctly, we will go to the initial values and we are going to change the temperature to be the initial temperature. Now we are done with the heat transfer part and we'll be moving to the multiphysics. For the multiphysics, what we are doing is simply we are coupling these two models. We have the lambda battery and we have the heat transfer in solids, and each one of them has their own equations, but we need to couple them using something called multiphysics. And in this case, we are going to add multiphysics coupling in this one, and it's going to be electrochemical heating. As you can see here in the electrochemical heating, we are coupling the electrochemical part, which has the lumped battery, and the second one is related to the heat transfer, which is the heat transfer in solids. Now we are remaining with only a few touches, and these are going to be the mesh and the study. And after that, we can compute this model. For the mesh, we'll go to the mesh, and we can select mapped. Or we can just simply right-click in the mesh here, and we can choose mapped. And we are going to do some adjustments here where we will clear this box. And we will go to the mesh one and we'll click build all. Now we have the mesh ready and we'll be moving to the study. For the study, we are going to specify the output times, which is simply the duration of the simulation. And this will be from 0 to 2100. And for the tolerance, it will be user controlled 1, and that will be 1 times 10 to the power minus 3. After that, we will show the default solver, which is this one, and we'll expand the nodes till we reach the time dependent solver. And from the times to store, it will be steps taken by solver. And that's it. We are ready. So now we can compute. Now we have the results. We mainly need to clean them to have them ready for the final outcome. And for this graph, we are going to expand the node and we are going to disable global to graph. Sorry, it's not delete, it's disable. And now we will modify the title of this figure. And the legends will be in the lower right. Now we have this plot ready and we can move to the next one. And this plot, as you can see here, it's performed at time that's equal to 2100 seconds. So it is at the end of the simulation, so which means after the relaxation time. But what we are interested in is at that time that's equal to 1500. And to get that, we'll go to the time and we'll choose interpolation because we don't have the 1500 time ready for us here. Okay, so we will choose interpolation and we will type 1500 and we will plot this one. So now we have it in this way. And the last graph we are interested in, which is the one where we use the probes. This one, which shows the minimum, mean, and maximum temperature across the battery. The first thing that we're going to change will be the label. And for the title, we'll choose manual, and it will be temperature change. After that, we'll type in the y-axis label, which is delta T. Now we'll modify the legends, and we are going to expand this one and choose probe table graph 1. We will go to the legends here. And it's going to be manual, and we are going to make the required modifications. To ensure everything is right, we are going to click plot this way. Okay, now we have reached the end of this tutorial until here. For the appendix, this one is regarding the geometry modeling instructions, which we have done at the beginning of this video.